This is going to be our third video on chemical reactions, and here we're going to talk about oxidation-reduction reactions, or sometimes redox for short. And I think the concepts that you're going to learn here are very important, and you'll use this again, some of this again, in chemistry too, when you get to electrochemistry. So what is a redox reaction? Is a reaction involves the transfer of electrons from one chemical species to another. Okay, that's the definition. It involves a transfer of electrons. Okay, or a reaction that involves a change in oxidation state or oxidation number. It's sometimes used interchangeably. Change in oxidation state or oxidation number of the chemical species involved. Okay. So oxidation, the definition of oxidation is loss of electrons. You want to stay away from definitions like this is where electrons flow in or this is where electrons flow out. No, the definition of oxidation is it's a loss of electrons. Okay, so for example, when a sodium atom becomes a positively charged sodium ion, that's oxidation, because electrons are given up. Because if you remember, positive ions are formed by the loss of electrons, right? For example, your sodium atom has atomic number 11, so it's 11 protons and 11 electrons, but the sodium ion is formed by the loss of one of those electrons. So it has 11 protons but only 10 electrons, and that's why it carries the positive charge, but that's the loss of electrons. All right? And then reduction is the gain of electrons. All right? So if a chlorine molecule picks up 2 electrons and becomes 2 chloride ions, that's reduction. Note that in the oxidation, electrons are lost. They appear on the right side of the equation. And in the reduction, electrons are gained or consumed, and that they're appearing on the left side of the equation. Okay, so a mnemonic that I've seen used is LEO GER, which stands for loss of electrons is oxidation and gain of electrons is reduction. Okay. Now, the oxidizing agent is what causes oxidation to occur. That is the substance that itself reduced. Okay. Now, matter has to be balanced in any chemical reaction. You have to have the same matter on both sides of the equation. And this extends down to the level of electrons. All right? So if electrons are being consumed in a reduction, where are those electrons coming from? They're coming from an oxidation. And that's why you can't have one process without another. So the reduction, the oxidation gives up the electrons, and the reduction gains the electrons. So the oxidizing agent, what causes oxidation, is the substance that is itself reduced. And the reducing agent is the substance that causes reduction to occur, and that's going to be the substance that is itself oxidized. So let's talk about how you would recognize oxidation and reduction reactions. All right. So anytime a compound is formed from elements, doesn't matter what type of compound, ionic or covalent, if a compound is formed from the elements, oxidation and reduction are involved. So if you have elements on the left side of your equation, like this reaction, if you have elements on the left side and a compound on the right side, that's going to involve redox. All right. So remember that metals like to give up electrons and form positive ions. Metals tend to react by losing electrons, right? And that's because, remember that the noble gases have a certain number of electrons are more stable than others. And that's the number of electrons possessed by the noble gases, right? So the metals are all 1 or 2 electrons past the nearest noble gas. So to be like the noble gases, they give up electrons. So metals tend to react by being oxidized, okay? And nonmetals tend to react by being reduced or gaining electrons, okay? So the example here that I gave you is the production of magnesium sulfide from magnesium and sulfur. Magnesium and sulfur are elements. Magnesium sulfide is a compound. Now, in the magnesium sulfide, it's going to be an ionic compound, so the magnesium is going to be +2 and the sulfur is going to be 2-. So the magnesium is going from magnesium metal to magnesium 2+ ion. Okay, that's an oxidation. And the sulfur is going from elemental sulfur to sulfur 2-, and that is a reduction. Okay, now the reverse is also true. Anytime elements are formed from a compound, oxidation and reduction are involved. So in other words, if you take a compound and break it down and get the elements out, that's also going to involve oxidation and reduction. Okay, so for example, if we take salt, the sodium chloride, and we electrolytically break it down and recover the sodium and the chlorine gas, and that equation is not balanced, but don't worry about it. If we'd have to balance it, we'd have to put don't worry about it. Anyway, but the sodium is being reduced, right? Because here we have sodium as part of the compound sodium chloride. Sodium is going to be a +1 ion here. Okay, so we're going from +1 to 0. That's going to take electrons. That's reduction. So sodium ion, sodium metal is a reduction, and chloride ion to chlorine gas is an oxidation. Okay. Now, what might not be as obvious is that any change in the number of oxygen atoms attached to an element, all other things being the same central atom, the same charge, always involves oxidation or reduction. So for example, an increase in the number of oxygen atoms corresponds to oxidation. So for example, nitrite to nitrate is an oxidation. Okay. Now I said all other things being equal. We have the same central atom, which is in this case nitrogen, and we have the same charge. Both of those are -1 ions. All right. Similarly, the reverse is true, that a decrease in the number of oxygen atoms is a reduction. So perchlorate down to chlorate is a reduction. Again, all other things being equal. Same charge, okay, I'm sorry, not the same charge, which is a -1, and then the same central atom. So it would be useful. Now this I would think that you would kind of see why this is. Okay, this is not so obvious. Okay, how is this an oxidation if the charge is staying the same? And how is this a reduction if the charge is staying the same? To be able to answer this question, why is this an oxidation, you have to be able to assign oxidation numbers. Okay. So oxidation numbers are kind of like a way of keeping charge or keeping count of electrons in a molecule. Okay, it's pretty easy for a monatomic ion. When you start getting the polyatomic ions, it gets a little more complicated. So, for an atom, first of all, for an atom in its elemental form, the oxidation number is 0. All right, so how are you going to know? How are you going to know if it's in elemental form? Okay, if it doesn't carry a charge and it's not part of a compound. All right, so if you see, for example, Na by itself for sodium, that's elemental form for sodium. It's not carrying a charge, it's not part of a compound. Na plus is not elemental form for sodium because it carries a charge. That's not elemental form. And NaCl is not elemental form for sodium. Okay, so if it doesn't carry a charge and it's not part of a compound, so just the element by itself, will have an oxidation number of 0. All right. For a monatomic ion, okay, for a monatomic ion, the oxidation state is equal to the charge on the ion. So for example, sodium plus has an oxidation number of +1. A Cl minus has an oxidation number of -1. Okay. Now, if you're dealing with something like a polyatomic ion or molecule, then the sum of the oxidation numbers in the compound is 0 unless the compound is charged. And if the compound is charged, then the sum of the oxidation numbers equals the charge on the molecule. Okay, I'll say that again, this is important. If it's charged, the sum of the oxidation numbers equals the charge on the molecule. Okay, so there are some rules for assigning oxidation numbers. All right, so group 1s. Okay, group 1. Some of this we've kind of gone over already in previous chapters now. Group 1s, right? That's the alkali metals. Remember, we already told you that they form +1 ions. Well, that also means they have an oxidation number of +1. So the group 1, the group 1s have a charge of +1 or oxidation number of +1 in all their compounds. Group 2s, that's the second column, alkaline earth metal. Okay, alkaline earth metals. Okay, are +2 in all their compounds. Okay. Now hydrogen is kind of weird. As far as it's +1 in its combination with nonmetals. So for example, in things like, very common examples, things like water and ammonia, the hydrogen is going to be +1. Okay. But it can be -1 when combined with metals. So for example, hydrides, for example, in the form of sodium hydrides. For the purposes of general chemistry, most of the time you're going to see this case. Okay, but you need to be aware that it can also be -1 if it's combined with metals, okay, like sodium hydride. Now, fluorine is always -1. There's no exceptions to that. All right, so no matter what fluorine binds to, it's always going to be -1. Okay. Oxygen is -1 in peroxides, things like hydrogen peroxide, H2O2, or sodium peroxide, Na2O2. And it's generally -2 in all other compounds. Okay. Now the halogens, that's the very last group on the periodic table, fluorine, chlorine, bromine, iodine. These tend to be -1 with the metals, -1 with other halogens, with halogens lower in the group, but they can go all the way up to +7 when combined with oxygen. All right. So let's look at some rules for assigning oxidation numbers. All right. Let's look at sulfur trioxide, SO3. Okay, so one of our rules was that the sum of the oxidation numbers equals the charge on the molecule. There's no charge here. It's not SO3 plus, it's not SO3 minus, it's not SO3 2 minus, there's no charge. So the sum of the oxidation states has to add to 0. So we have a sulfur, and we have 3 oxygens, right? And all that has to add up to 0 because it doesn't carry a charge. Okay, well, we didn't have any specific rules for sulfur, but we did say that oxygen is always, or almost always, -2 unless it's a peroxide, right? So to make all this add up to be 0, the sulfur has to be +6. All right, so the sulfur's in the +6 oxidation state, oxidation number. Okay, let's look at nitrite. Okay, nitrate rather, NO3 minus. All right, so we have a nitrogen, and we have 3 oxygens. And now, this is a polyatomic ion. It carries a charge. So the sum of the charges has to add up to -1. All right. So if oxygen is almost always -2, that means to make all that add up to be -1, the nitrogen is +5. Okay. Now the next example that I gave here is nitrite. Okay, now we follow a similar logic, just take away one of your oxygens. It's one less oxygen. It's NO2 minus as opposed to NO3 minus, right? So your nitrogen has to be an oxidation number of +3. And now you can see why, you should be able to see why with one of my previous slides, I said, all things being equal, when you increase the number of oxygens, you increase the oxidation state. This is why. Because oxygen adds to the oxygen is always -2. So NO2 minus to NO3 minus is an oxidation of the nitrogen from +3 to +5. Okay? And then my last example here that I gave you is perchlorate ion. Okay, again, it's a -1 ion, so the sum of the charges has to add up to -1. It's 4 oxygens. Okay, so 2 times 4 is, it's -8. So to make it all add up to -1, the chlorine has to be in the +7 oxidation state. Okay, so we talked about a couple of examples. Of redox reactions. I said anytime you make an element, anytime you take a compound and decompose it into elements, it's redox, or vice versa. Now there's another class of reactions that involve oxidation and reduction that involve what are called single replacement reactions. Okay, so this involves the displacement of an element from its compounds. There are several examples of this. All right. So many metals can displace hydrogen from acids. Okay. And I'm going to write, before you go any further, I'm going to write this. Your general formula for a single displacement is an element plus the compound is equal to a new element plus a new compound. Okay, so prime example, many metals displace hydrogen from acid. So for example, if you have hydrochloric acid, a solution of hydrochloric acid, even dilute acid, okay, you put zinc metal, okay, you'll put in zinc metal, it'll bubble, you'll see effervescence, you'll see lots of bubbles coming off. The bubble coming off is hydrogen gas. Okay, that's one way to make hydrogen gas in the laboratory. But the zinc is displacing the hydrogen from the acid. So in other words, zinc is the element that we're starting with. Okay. Hydrochloric acid is the compound that we're starting with. The new element that's produced is hydrogen. Okay. And the new compound that's produced is zinc chloride. All right. So basically the zinc is going in and kicking the hydrogen out of its compound. Okay. Well, you should be able to see why this involves oxidation and reduction. Okay. What's the oxidation number of the zinc here? That is zinc in elemental form. Doesn't carry a charge. It's not part of a compound. And that's oxidation number 0. Okay. Here we have hydrochloric acid. The hydrogen is going to be +1. Okay, hydrogen is going to be +1, and the chloride is going to be -1. Okay, here we have zinc chloride. Chloride is -1, so to make the oxidation numbers balance, the zinc would have to be +2, and then we have hydrogen. Now that's elemental form for hydrogen. It doesn't carry a charge. It's not part of a compound. That is 0. All right. So you can see why this involves oxidation and reduction. The hydrogen is being reduced from +1 to 0, and the zinc is being oxidized from zinc elemental form 0 to zinc as part of a compound. So I'll say that one more time. The hydrogen is being reduced, and the zinc's being oxidized. Okay. But basically, the zinc is going in and displacing the hydrogen. Okay. Now, some metals can displace hydrogen even from water. It's a similar type of reaction. You're displacing hydrogen, but now you're displacing hydrogen from water. If you throw calcium metal in some water, again, you'll see lots of rapid effervescence. That effervescence is hydrogen gas coming off. Okay, basically same thing. The calcium is going in and displacing the hydrogen from the water, right? So the calcium would be our element, the water would be our compound. Okay, calcium hydroxide would be the new compound, and the hydrogen would be the new element. Okay. And third thing is some metals can displace other metals from solution. So for example, if you go in and put zinc metal, right, solid, there's no charge here, it's not part of a compound, so that's zinc metal, that's zinc in elemental form, and you put that in some copper containing solution like copper sulfate, copper nitrate, counterion doesn't matter, a solution that contains copper ion, you'll get a reaction. Okay, you start with copper ion and zinc metal, and you finish with copper solid in zinc 2. So this is another single replacement. The zinc is going in and displacing copper as part of its compound. Now everybody's familiar with copper because pennies are made out of copper, or at least they have a copper shell around They used to be made out of pure copper, and now it's just a copper plating. But anyway, everybody's familiar with copper. It has that reddish color to it. Okay, as this reaction proceeds, that copper is going to start plating out. In other words, you'll have copper metal being produced from the solution. At first, it might look like your zinc strip, and zinc looks kind of silvery like aluminum. Okay, and what's going to happen is copper will start plating out. It might stick to the zinc, but it might fall off. But you'll see, the reddish color. The copper in solution picks up those the two electrons that zinc is giving up, and it's being reduced to the copper metal, and it's basically falling out of solution, right? So the zinc is oxidized. From zinc to zinc 2 is an oxidation. And the copper is reduced. From copper 2, the copper metal is a reduction. So all these reactions involve oxidation and reduction. Okay. So your activity series is basically a listing of the tendency for things to be oxidized, or reduced. All right. The elements at the top here have a strong tendency to be oxidized. Okay, so what you're ranking here is the tendency to be oxidized. So the elements at the top, like lithium and potassium, and is the calcium that we mentioned in a previous example, they all have a strong tendency to be oxidized. Even zinc has a fairly strong tendency to be oxidized. Okay, we move down here, we get to the metals that don't have such a tendency to be oxidized. Things like copper, silver, mercury, platinum, gold, and so forth. Now, what do you think we like to use? Why do you think that we use plumbing? That we use copper for plumbing pipe? Why do you think that we like to make jewelry out of silver and gold? Because those elements, those metals, have little tendency to be oxidized. Okay, it wouldn't do you any good to make jewelry out of zinc if it's going to discolor and oxidize. Okay, so the higher up you go, the stronger the tendency to be oxidized. So a single displacement, like the reaction between the copper and the zinc, we can predict whether such a reaction will happen or not. It's very simple. One element can displace another if it lies above it in the activity series, right? So back to the previous example, copper and zinc, right? Okay, so here is zinc right here, okay, and here is copper way down here, okay? So zinc can displace copper, okay, because zinc lies ahead of copper in the activity series, okay? So let's use the activity series to predict whether each reaction would occur. Now this one we already did. That was my example from the previous slide. You're going to put a piece of zinc metal in copper. The zinc is oxidized. Zinc's displacing the copper. Okay, yes, that reaction can occur. Okay, but what about this one? Okay, silver and zinc, right? So we have a solution of zinc, and we have silver metal. Now, if you go back and look, let's go back and look at that activity series for a minute. I had already mentioned silver. Silver is down here near the bottom. Okay, it doesn't have much tendency to be oxidized. Zinc is up here, silver's way down here. Silver can't displace zinc because it lies below zinc on the periodic table. So that reaction is not going to happen. And here's a last example. Could copper displace hydrogen from acid? Okay, So the copper would be oxidized and the hydrogen would be reduced, but if we find the hydrogen reaction, it's here, and copper is below hydrogen. So copper is less reactive than hydrogen, so basically copper cannot replace hydrogen from acid or from water. Okay, so just a couple of more things here that I want to talk about. Okay, composition reactions, and now we're just talking about, we're not classifying reactions here now by the chemical principles behind them, but rather by the type of reaction. So, for example, a composition reaction involves the formation of a molecule from simpler molecules or from the elements. Now, such a reaction, it might be an acid-base reaction, it might be redox reaction. A lot of these, and probably the most common reactions of this type you're going to see are going to be redox reactions. So, for example, production of magnesium oxide from the combustion of magnesium metal. Magnesium will burn. Okay, you light it up, magnesium will burn. Sometimes powdered magnesia is added to flares, or not to flares, but to fireworks to give off a white light. Or old style flash bulbs, which most people have probably never seen at this point, had fine magnesium ribbon in a glass bulb that was filled with pure oxygen, okay, and make the reaction go even faster. But anyway, this is a combination or a composition because you're making a compound, okay. In most composition reactions are going to involve redox, okay. I can think of some that might involve acid and base. It would involve acid and base, but most of these are going to be composition reactions. And then last, this is our last slide. The last is a decomposition reaction, which is the opposite of a composition reaction. Okay, so this one involves the decomposition of a molecule into elements or even into simpler molecules. So, for example, if you heat mercury oxide, so orange-red powder decomposes it gives off oxygen and decomposes into mercury metal. Note the L there. That means liquid. Mercury is one of the few elements, and it's the only metal that's a liquid at room temperature. But anyway, it gives off mercury liquid and oxygen gas. Or another example, and obviously you should be able to see that involves oxidation and reduction, right? Because we're taking a compound and breaking it down and getting the elements out. Okay, that's going to involve redox. Now, potassium chlorate, KClO3. You can heat that. If you heat it gently, I would not advise heating it strong. In fact, I'd not advise playing with this stuff at all. But anyway, if you heat it gently, it decomposes into potassium chloride and gives off oxygen gas, right? That's a redox reaction. It's a decomposition because we're taking a compound and breaking it down into an element and a simpler compound, right? But that's also going to involve oxidation, and that's also going to involve oxidation and reduction. So nearly all composition reactions involve oxidation and reduction. And we'll stop here for this video.